We can represent this vector using this two-dimensional column matrix. It shows that we are adding 3 of these vectors with 4 of these ones to get the yellow vector. If we call these two vectors A and B, this one is the scaled version of the first vector, and this is the scaled version of the second. So this vector is simply the addition of these two scaled vectors. By using these two vectors, we are seeing this two-dimensional plane with these grid lines. And we can write any vectors on this plane in terms of the linear combination of the two vectors A and B. Lambda 1 and lambda 2 in this linear combination are two real numbers that scale the two vectors A and B. In this case, we say the two vectors A and B span the whole plane, or this two-dimensional space. And this set of linearly independent vectors that generate the whole space is called a basis. Now, let's take the vector we talked about again and forget about all the things I said. What if I take these two vectors? By choosing this basis, we see this two-dimensional world like this. In this basis, we can use these two numbers to represent the vector. Pay attention that the first number corresponds to A and the second one to B. So we can write it as a linear combination of two basis vectors. Pay attention that A and B, our basis vectors, correspond to these two column vectors in this coordinate system. So far, we have talked about these two sets of basis vectors that form two different coordinate systems. They can both span the two-dimensional vector space or the whole two-dimensional plane. And in each coordinate system, the same vector is represented using different coordinates because the basis vectors are different in them. This basis, by convention, is called the canonical or standard basis, for which A and B are unit vectors and also they are orthogonal. But pay attention that also in this case, A and B are presented using the same two-dimensional column matrices. In this coordinate system, the unit vector is different, and in this framework, the world is different. There's a way to change these two bases, but for now I'm not going to talk about it. So, this is a standard basis for this two-dimensional vector space, but these are also different sets of bases in this two-dimensional vector space. Each of these sets of bases can generate all the other vectors in this vector space. So, in case of two-dimensional vector spaces, when we have two linearly independent vectors, which are two elements of the vector space itself, we can write any other vector in this vector space as a linear combination of these two basis vectors. In other words, our vector space is a span of these two basis vectors. And using these two basis vectors, our two-dimensional vector space looks like this. The basis vectors help us talk about the whole vector space and create new vector based on them. Somehow they're like a framework by which we can see the vector space. Pay attention that in this framework, A1 and A2 can be represented by these two column vectors and can form all the other vectors as linear combinations of them. We can also get back to the standard basis for this vector space, and in this case, A1 and A2 are represented differently by two other column vectors. Let's add another dimension to our vector space. Now we have a three-dimensional vector space. If we add another vector that is not in the same plane, or in other words cannot be written as a linear combination of the two other vectors, we say that these three vectors, A1, A2, and A3, are linearly independent. And we can span the whole three-dimensional vector space using these three basis vectors. In other words, we can write any vector in the 3D vector space as a linear combination of these three vectors. A1 and A2 also span a subspace U of our three-dimensional vector space. It means that there is a subset of vectors that can be spanned by just these two vectors, and they, geometrically speaking, form a plane in the 3D space. Pay attention that we can't say these two vectors A1 and A2 span the two-dimensional vector space anymore, because the vectors A1 and A2 are still elements of a three-dimensional vector space and are denoted by three real numbers. So this is a standard or canonical basis for this vector space, and these are some other bases. There are three elements in each set. They are linearly independent, so they can span the vector space. Now, you might say, I don't trust you. How should I know this set of vectors are linearly independent? I've thoroughly explained it in this video, but in a nutshell, if you want to see if a set of vectors are linearly independent, you first put them in a matrix like this, in which each column of a matrix is one of the vectors. Then we change it to the row echelon form by some row operations I have explained in one of the previous videos on this playlist, and if all the columns are pivot columns, it shows that our vectors are linearly independent, and so we can use them as a basis to span the vector space. Sometimes a set of vectors like these are not linearly independent. If we arrange them in a 5 by 5 matrix like this and change it to its reduced row echelon form to see how the vectors are dependent on each other, we find two pivot columns that represent the independent vectors. Let's check the meaning of all of these columns in the reduced row echelon form. The first two columns suggest that A1 and A2 are linearly independent. So we can use these as two basis vectors to span a subspace of a 5-dimensional vector space. In other words, we have a 2-dimensional plane in a 5-dimensional space. The next three columns show that we can write the remaining vectors as a linear combination of these two basis vectors of the linear subspace U. So A3, A4, and A5 live on the same 2D plane in a 5-dimensional space as A1 and A2. Now take these 5 vectors. How many of them are linearly independent? Again, by putting them in a matrix and changing the matrix into reduced row echelon form, you can see that now there are 3 pivot columns that represent the independent vectors. So the first, second, and the last vectors are independent. And we can write the third and fourth vector based on the first 2 vectors. This time, this set of linearly independent vectors span a 3-dimensional subspace of our vector space. It means that the linear combination of them can give all the vectors in a subset of our vector space. For this set of vectors, which are only different from the last one by these 2 elements, we see that the reduced row echelon form matrix is diagonal, which shows that all the vectors are linearly independent, and their linear combination can give any vector in this vector space. So, if we have a vector space V and also a set of vectors in this vector space that their linear combination gives any vector in this vector space, we call this set a generating set which spans the vector space V. Also, a generating set is called minimal if we can't find any smaller set that spans the vector space. We call this minimal set the basis of the vector space. In other words, a maximal linearly independent set of vectors in V is called a basis for this vector space V. Pay attention that this minimal generating set, or in other words, maximal linearly independent set of vectors, is not unique, and we can have many of them as you saw in this video. Also, sometimes you might find a set of linearly independent vectors that only span a subspace of V. In this case, the number of these linearly independent basis vectors is not maximal, so they just span a subspace of the whole vector space.